Okay, so what we're going to talk about right now is the myelin sheath. The myelin sheath are these nice little white bundles that we see around the axon of all of your neurons here. They are mostly located in your peripheral nervous system, which includes everything except for your brain and spinal cord. All right, so as you have probably noticed, walking through the activity with the beads is that it takes a really long time to go from one paper to the next paper to the next paper, because all of these sodium and potassium ions gates have to open and close and open and close. Then we reset, and it just kind of goes on and on and on, and it takes a really long time to make its way down the line. Well, the same is true for the axon. It doesn't change since we're in a neuron. It takes a very long time to get the message all the way down those axons, and the longer the axons are, the longer it takes to get the message down. Now, the nervous system is there for a reason. Yeah, it's there to control what you're doing, but if you remember, one of the characteristics of the nervous system is that it has to be very quick, and it needs to be able to reset quickly as well. So how does it do that, since it takes forever to open and shut these gates and then reset them and then move to the next one? So we have this thing called the myelin sheath, and the myelin sheath insulates the axon of the nerve cells. And what they are individual cells called Schwann cells. And these Schwann cells, I'm going way over here. I hope that is far enough out of the way. Okay, so the Schwann cells are these goofy little cells, and what they do, and they're full of cytoplasm and all of that good stuff that cells should have, but they go through and they wrap themselves around the axon, just like this, until they roll, 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 roll. And so you can see here when it's done that it's insulating this section of the neuron. So if I come over here, I can see that this white section right here is one Schwann cell that's wrapped around. Then next to it is another Schwann cell that is wrapped around, and then another and another and another, and it continues on in that fashion. But what we see here is that we have these little gaps that are in between the nerve cells, and that is called the nodes of Ranvier. Okay, looks like nodes of Ranvier, but it's pronounced Ranvier. Okay, French or something like that. All right. So what does it do? Well, it speeds up the signal, because remember, what is activating those gated ions to open is the change in the membrane potential. When the negative goes to positive or the positive goes to negative. That's activating those gates to open. But if I go through and I cover up the gates right here along the neuron, we cannot activate those gates to open, because they are not sensing that change in action. They're not sensing the change in the voltage. All right, so what it's going to do is it's going to allow us to speed up the signal. So how does that do that? Well, because as I go through here, what we see happen is that we now can jump from exposed section of the ion or axon to the next one. And so we go jump from here to here to here. So now what we see is that the only gates that are open and closed are the ones that are actually exposed to the surrounding solution, and those are only at those nodes of Ranvier. So as the information comes in here through the axon, in here through the dendrites, the message comes in. Remember, these are the ligand gated channels that are being opened. If the stimulus is hard enough, so we have put our hand on a hot stove, or we have pelted this dendrite section with enough neurotransmitters to get to that threshold membrane, that threshold potential, then we're going to start to see those gates start firing open, action potential, all the way down through the cell body. We're going to get here. And now, instead of having to go all the way down and open up all the sodium ions as we start to move down and change the gradients as we move through, we now only have to change it in this location. And when we change the membrane potential and it becomes positive on the inside and negative to the outside, that is going to travel through the axon or through the cytoplasm of the nerve cell. And the next section that's going to be activated is going to be here, is this exposed section. And then it can go to the next one, and to the next one, and to the next one. Okay? Oh, there we go, it jumped again. All right, so we're jumping from node to node to node. Okay, so what does that do for the nerve cell or for the transmission of this action potential? Well, it takes it from and makes it about 150 meters per second that this action potential can travel versus 5 meters per second. Okay, so if we were to translate that into something we can comprehend, we take a nerve or an action potential that normally would travel 11 miles an hour and speeds it up to 330 miles per hour. That's quite a difference. Okay. All right. So the myelin is insulating and it prevents the passage of ions during this section where we are covering the axon membrane, okay, because we are not coming in contact with the solutions that are surrounding it. All right, here are your nodes of Ranvier. Okay, these are the sections here that are the gaps between where the Schwann cells are wrapping around the axons. Okay, in this section right here, you can see the ions are traveling, the membrane potentials are changing, but as they change, it's not just in that section, it travels the length of the axon on the inside, triggering the next section down the line, the next section of gates to open up. Okay. All right, again, another picture. This is a section that is actually referred to as saltatory conduction, okay, and that just means that we are jumping from node to node. All right, so if I go back into the paper activity that we did, where Bryn, you are sitting there and you are manipulating your paper worksheet, so you're moving your beans in and out, in and out, and in and out of the cell. Or I threw the volleyball to Bryn and she has to do 10 jumping jacks. Once she is done with her 10 jumping jacks, she can pass the volleyball to Marley, and Marley, you have to do your 10 jumping jacks. And before you can go and do your next 10 jumping jacks, you're going to go to and pass the ball to Gunnar before he can do his 10 jumping jacks. So now what we're going to do is that while you guys are going through and doing all your jumping jacks, what I'm going to do is I'm going to pass the ball straight over to Gunnar, and we're going to skip Marley and Bryn here in between. And Gunnar is going to write his hello signal on the paper. It is much faster to skip the in-between people. But we can't skip too far. The nerves are too long in order for us to do that. Okay, so the question is that what happens if we take this myelin sheath away? If we take the myelin sheath away, the message is still going to make it from point A to point B. We are just going to slow it down. And so people with multiple sclerosis, this is exactly what happens, is that their immune system is starting to attack the myelin sheath. It's going to deteriorate these cells, and it's going to uncover the axon length. Okay, so we are now back to everyone has to do their jumping jacks before Gunnar can write the word hello. All right, so the message eventually will get to the bottom of the axon, or to the end of the axon. It's just going to take a really long time to get it done. And so this is why when we see people with multiple sclerosis, they have a really hard time, depending on the progression or how much of the myelin has disappeared, what their movements are. Their movements are jerky. Sometimes they can't walk. And it's not that the message isn't getting to the muscles to tell them to walk. It's just that it's taking a really long time to get there. And so the coordination between the brain and what the brain wants to do and what the muscles can respond to is very slow. Okay, and they're not all on the message is not all getting there at the same time. Okay, so we have a loss of signal. Okay, it takes a really long time to get there. All right, so this is known as saltatory conduction. I'll show you a quick video on it, and then we should be done. Maybe I'll show you a video.
The improved efficiency is due to the fact that the insulation provided by certain cells, called Schwann cells, which have wrapped themselves around each axon, effectively limits the movement of ions to short segments between these cells, rather than allowing this ion exchange to take place along the entire length of the nerve fiber. Loss of the myelin sheath can cause serious impairment of function of the nerves involved.
Okay, and so that's the myelin sheath, and I hope that you have learned something.